Okay, so I will be talking about isolation, and I'm sorry, I tried to make it entertaining, but that's a pretty academic, fundamental topic, so sometimes I have to be very theoretical, and I'm very sorry about that. Normally, I try to have my slides about unicorns and kittens. It won't be the case here, but I still try to explain things as I understand them. And of course, you can't explain something if you don't understand it, normally. First, about who I am. I'm Lætitia Avrot. If you can't say it correctly, that's normal because you're not French. But it's not a problem. If Lætitia is too difficult to say, you can say Joy because that's the same name in English. I'm a field CTO at EDB. If you don't know what a field CTO is, it's a CTO without any management responsibility, but a lot more tech responsibility. About slides. So you're not missing a lot about my slides because the one I present normally are without words. Because I'm a mom, and when I talk, I like to be listened to. And I found out that when there were words on my slides, people were reading my slide and not listening to me, which is awful. So I decided to remove every word from my slides so that people have to actually listen to me. But I know that some people have some other things to do, other things to think, or even hearing troubles or ADHD or whatever other reasons that can make it very difficult to follow. So if for whatever reason you need more words, just go to mydbanotebook.org. And for that, if we can't fix the problem here, when we will go deep into technical, I really encourage you to do that. mydbanotebook.org, you will find a Conf Talk tab, and then you will have access to the slide. Actually, it's not the same slide that I'm presenting. Well, not presenting, but you will have words, a lot of words, which can help you to understand me better because of my accent, because of, whatever reason. So that's on mydbanotebook.org. And the last thing you might want to know about me, I'm on Twitter, @L_Avrot. I try to tweet about databases, Postgres, but it's my personal account, so sometimes you might see a raccoon trying to wash a cotton candy and being very disappointed or things like that. So let's go straight into the subject, acid. So the acid properties were kind of invented by Jim Gray, who won actually an award Turing back in 1998 for his work in databases. And actually what Jim Gray thought back in the late 70s was that a relational database needed atomicity, consistency, and durability, but no isolation. And if you worked with DB2, that shouldn't surprise you because we see that DB2 does things that as Postgres might think as atrocities. But the isolation concept was adding later in 1983. So first, just to make sure we're on the same page, I will quickly review the concept of atomicity, consistency, isolation, and durability. So atomicity is the fact when you have all or nothing. An atomic transaction is an indivisible series of database operations such that everything occurs or nothing, but you can't have just portions of it. Consistency refers to the requirement that any given database transaction must change affected data only in allowed ways. Allowed meaning when you have constraints, you have to make sure they are fulfilled, and so on. Isolation determines how transaction integrity is visible to other users and systems. And durability is a property that guarantees that whatever happens, if you had a common acknowledgement, your data can't be lost. Wow, that's a huge device just. Okay, so as I say, isolation normally is a way to have transactions working concurrently but without interactions. But we found out that if we wanted everything to work concurrently without any interaction, then we had very big troubles called locks, and then we had an increased latency, which was not most of the time something we wanted. So we defined what we called isolation levels. There are 4 isolation levels. The first one is read and committed. It means that a transaction can read a change that is not yet committed by another transaction. That's the kind of atrocities I was talking about later. Postgres does not allow that, even though you can set your isolation level to read uncommitted. But in the end, Postgres will just use the next level, which is read committed. Postgres will never allow you to read data that are not committed yet. The next level, so we have read uncommitted, we have read committed, and the next one is repeatable read. Imagine you have a transaction going on, you read a data, then you keep going, and there's another transaction happening and changing the data. So in your first transaction, when you try to read again the data, it won't be the same because it was changed and committed by another transaction. Sometimes it's acceptable, sometimes it's not. If it's not, it means that you need to change your isolation level to repeatable read so that you're sure that each time your transaction will read that data, it will be the exact same data. And the last one is serializable. It's the level where we emulate serial transactions so that we are sure that there is no interaction between transactions. If a transaction tries to change the data and another happens trying to change the same data, it won't be able to do it. There will be an error, and you will need to retry after. It really tries to serialize any transaction one after the other so that you won't enter any anomaly. So I will be talking about isolation anomalies. So that's exactly what we're trying to avoid when we are having a higher isolation level. And the first one we might want to avoid is called dirty read. A dirty read is when a transaction reads data written by concurrent uncommitted transaction. So again, Postgres won't let you do that. I know that DB2 allows you to do that. There might be other RDBMS outside that can help make you do that. But that's not a possibility with Postgres. So I had a great illustration with transactions. So I will try to explain, or maybe I could draw. I will try to draw on the board. Maybe that's something I can do. Can you give me a pencil? Because that's something very visual. And it's difficult to, yeah, I don't need that much. Let's say you have one transaction here, which is, for example, you have some money on your bank account, like you have 50. And so that's your bank account. And you have a level of 50. And then you have someone from your household who does something as stupid as grocery shopping or something like that. And so you have the beginning of the transaction here, and then they will retrieve 100 from your bank account. There is an integrity constraint saying that you can't have a negative number here, but some integrity constraints are checked at the commit when commit happened. So for now, it will be okay with having a bank account level of -50. And let's say that you're outside shopping and you find these great shoes that you want to buy. And these great shoes are only $49, which is great for shoes, if you know what I'm saying. So here, you want to pay your great shoes, which is a great offer at $49. So it will take this bank account, and then it will do that to your bank account. And then this commits, well, try to commit, but it has to roll back because of integrity constraint. And so you will come back with 50. And then here, you try to commit, but it will still roll back saying, no, you are at -99, so you can't do that. And you won't be able to buy these perfect shoes for you, which is a pity. And so you will be back to your 50. And that's an anomaly, because normally you should have been able to buy the shoes. Grocery shopping is not important, but the shoes are. So that's the kind of anomaly you can get with dirty raid. The next anomaly we will look is called lost update. It's a data integrity problem in which one writer of data overwrites the changes of a different writer, modifying the same data. So if I want to explain, let's say, again, you have a bank account. So I don't want to mess up this one. So you have a transaction. You have your bank account with 100, let's say, $. Normally it's euro on my demonstration, but will be the same. So you have a transaction that begins. And then what you will do is retrieve $50 from your bank account. So that's which should be 50. And then you have another transaction beginning here. And let's say that you, again, want to retrieve $50. And so here it was reading here. Here it is reading here. So it does 100 minus 50, it's 50. And so when you commit here, you will find that your bank account is 50. And when you will commit here, which is a load, you will still have a bank account of 50. So it means that here you have an anomaly because you were able to retrieve twice 50, and you still have 50, whereas you had 100 before. I'd like my bank to do that. They don't. After that, we have another anomaly to explore. It's called non-repeatable read. So let's say, again, you have one transaction which begins here, and then the first thing the transaction does is display the stock, just to say if, for example, the item you want to buy is there, or if you will have to wait for 3 weeks to have it. So it will tell you that the stock is 1. And then there's another transaction coming. And as you've seen that the stock is 1, you say, OK, I can put it in my cart. And at the same time, this transaction will read the stock, and it will see that it's 1, because it's in the cart, it's not committed yet, so the stock is still 1. And what happens next is the person is happy that it's in stock, so it will put it in the cart also. And what happens after is, should that one commit here, then the stock will now be 0. And when that one will try to commit, it will say, oh, no, the stock is now 0. So you can't commit. You have to roll back. That's another anomaly. And if you think that it can't happen in the real world, I can tell you it does, because I've experienced that a numerous of times during lockdown when we were grocery shopping online, and they had done nothing to prevent that. So I was doing all my grocery shopping, and at the end, when I was looking at my card, it was saying, oh, no, there's no more that, and I had to redo my grocery shopping, which was very infuriating. So that's something that can happen, and I really like people from Carrefour to learn from that. So this is called non-repeatable read. Then that's my favorite, because the name is so cool. It's called phantom read. It's when a transaction re-executes a query, returning a set of rows, but without changing the search condition, but the result is different. So to explain it, let's say that you're shopping for books here. So you begin your transaction here, and you're searching for books with the name Slonik in it. And it tells you, OK, there's 11 books with the name Slonik in the title. So what happens next is the librarian, not the librarian, but the manager of the bookshop finds out that there is a duplicate. The Life of Slonik is written twice, whereas it should be only once. So what they do is they begin a transaction, they delete the duplicate, and they commit. The thing here is, OK, you found 11 results, but there is a pagination system. So it will only show 1 to 10 books. So you browse the result, and you say, I'd like to see the next page. But as you're a human, it takes you a little time to process the 10 first results, so that the commit happened before you click on the next page. Then it will resend a query, and then it will say, oh, no, there's no next page. And you will find a 404 error. That's a little infuriating, because there was 11 results, and now there's only 10. And it even can't tell you there's only 10 results now. What the application typically would say is just that this page does not exist, and you will have to redo it from the beginning. So that's what phantom reads are about. The last one is one of the most complicated transaction isolation anomaly. It was discovered only in 2003, whereas we were working with transaction isolation since the late 70s. It probably occurred before, but it was only theorized in 2003. And, well, we all know that sometimes we don't understand bugs, in particular bugs with data, and that we don't have the time to really understand in depth what's going on as long as it's fixed. So I guess that's what happened with mode serialization anomaly. So a serialization anomaly is when the result of successful committing a group of transactions, the result of successfully committing a group of transactions is inconsistent with all possible orderings of running those transactions one at a time. So I will explain with an example. It will be much clearer. So let's say you have 3 types of transactions. It's a restaurant, and in this restaurant, we have a transaction called new ticket. During that transaction, we will, of course, begin. And then we will read the day. And then we will add a ticket to the day that was read here. And we will commit that. That's how we add a ticket when we have a new receipt for a new table in the restaurant. So let's say from time to time, we have to say to the system that there's a new day. So to do that, we have another transaction called new day. And this transaction simply takes the begin, update the day, and commit. Normal, we just do +1 on the day, and then we're registering the new day. And the last transaction is when we try to have the daily imbalance for the restaurant so that the accountants are very happy. So daily imbalance is a transaction where we begin, we read the day, oops. And then after reading the day, we will sum all the tickets and write the imbalance. So you will sum all the tickets of the day. We will write the imbalance. And we'll commit. So when we take those separately, there's no problem with it. The problem comes when they are executed in a very specific order that will make them wrong. So let's see how we can mess up these 3 transactions. So first, let's say there's a new ticket. Begin. And then as the new ticket transaction, the first thing it does is reading the day number. So we read day. Then the second transaction, the new day transaction, begins because actually it's very late and it's the time to have a new day. So we have a new transaction that begins, let's say it begins here, and it will update the day, and then commit. Then we have the third transaction. So that's the daily imbalance. Let's say it begins here. And then we read the day number. Let's say we read it here before a commit. So that if here it's the 21st of September. Sorry, you're American, you use that date wrong, but anyhow. And here we are, oops, that's messy. We are the 22nd here after the commit, but here when we read, we're still the 21st. So we read the 21st here, and then, so we will add a ticket. And let's say here, we will write the imbalance of the day before. Here, it's not committed yet, so we can't take into account that ticket. So when we will write the imbalance, as it's not committed there, we can't see that one. So there will be a missing ticket. And there's no way we can make it right. The only way to make it right is to have each transaction working one after the other. But if we want to intricate them, there is no way it can end up with the right day, with the right imbalance, with the right day for the ticket, and so on. And that's why it's so complicated. That's why we need at least 3 transactions to display it, because it's really not that simple. And so what we could do, for example, is instead of writing here the imbalance, what happens if we read the day here? So if we read the day here, after the day change, then we won't have a missing ticket, actually. That won't be the problem here, because we will write the imbalance too soon for the 22nd of September, where we have no ticket, so the imbalance will be 0. And we won't have any imbalance for the 21st of September. So that's another way to mess up things with these 3 transactions. So to sum up, I guess it will never work. I will try to sum up how you can take care of these anomalies. As I say, you have 4 isolation levels. So I will do a table. So isolation levels, and then we will see the anomalies. So the isolation levels you have, the first one is red uncommitted, sorry. The second one is red committed, and I will be too short.
That's what I'm here for.
Right? No, black is better. Repeatable read.
I got it.
And you need some to leave some room for serializable. Oh.
Oh, beautiful.
Oops. So if I can just use, it will be easier to display the table directly. So this is the annotated slide deck. I will use the presentation slide deck, but feel free to go to the annotated. And we're there. So I've already displayed all the transaction thingy. Okay, so with the isolation level red uncommitted, you can have dirty red. With all the other isolation level, you can't have them. which is good. You don't want anomalies normally, but we'll see that there's a trade-off. Loss update can happen when you have read uncommitted and read committed. Non-repeatable read, same thing for read uncommitted and read committed. And the phantom read can happen if you have read uncommitted, read committed, and repeatable read. So this is purely, and serialization anomaly is the same than phantom read. So this is purely theoretical and should be true for any serious relational database system. This is what Postgres does. So the only difference is that you can't have the read uncommitted level, so that you can't have dirty reads. That's the only difference with Postgres. So you might ask yourself, why don't you do serializable all the time so that you can't have any anomaly? That's a problem with serializable. But first, let's talk a little about MVCC. MVCC means the multi-version concurrency control. It's a concurrency control method very commonly used by database management system to provide concurrent access to the database. Because I don't know for you, but the databases I've seen, it's very rare to have only one transaction at a time. Most of the time, we have hundreds or thousands of transactions happening at the same time. And it's that complex that human brains can't process it, actually. But what we've come out to try to make things right is we decided to use lock. Record locking is a technique of preventing simultaneous access to data in a database to prevent inconsistent results. It means that if somebody is already trying to change the data, you won't be able to access it and you will have to wait, which is great and not so great, depending on, because there's no way you can say that that transaction is priority and should have access before that one, and so on. And what happens logically with locks is deadlock. A deadlock is a state in which each member of a group is waiting for another member, including itself, to take action such as sending a message and more commonly releasing another lock. So if we try to illustrate it, let's say we have two data that are pink at the moment, data 1 and data 2. The first transaction begins and says that data 1 should be blue. And then there's a second transaction going on, says that data 2 should be green. What happens if transaction 2 says now data 1 should be green, and transaction 1 says data 2 should be blue? Then it won't be able to access the other, so that transaction 1 will be waiting for transaction 2 to release the lock on data 2, whilst transaction 2 is waiting for transaction 1 to release the lock on data 1. That's what we call a deadlock. And the only way to sort this out is to kill one transaction at random. That's exactly what Postgres does. So Postgres analyzes logs when there's a parameter you can set to say how much time it can wait before trying to analyze that. Each time it finds a cycle in the log pattern, it means there's a deadlock, and it will randomly kill a transaction until there's no cycle. So it will kill a transaction. If there's still a cycle, it will kill another one, and so on. Of course, that's something you might want to avoid, because killing transaction is not what you use your database for. So there are two general advices for developers to avoid that. The first one is to always change data in the same order. Don't try to change data 1, then data 2, and on the other transaction, data 2, then data 1. Always do in the same order, data 1 and data 2, or data 1 and or data 2 and data 1. The second general advice we can give is try to keep your transactions as short as possible. This will reduce the risk of deadlock very, very drastically. So Now that you've seen all this theoretical thing, you might ask yourself how you can make that knowledge valuable in your day-to-day work, because I'm pretty sure you've never seen someone running like, oh, we need to use a serializable level. No one says that. So how can you use that? Oops. That's because I don't have my speaker notes. And actually, most of the time, the committed read level should be enough for your usage. And you have to ask yourself what you can allow in your system. If you can allow yourself to have lost updates, then keep it simple and use the committed read level. And in 99% of the use case, it would be enough. There is one use case when you might want to use the highest level, which is serializable. It's if you want to have things like invoice numbers. You know that legally you're not allowed to have holes in a sequence of invoice number, and you're not supposed to change them afterwards because it could be seen as fraud. And you don't want your company to be accused of fraud, of course. So in that case, using the serializable level for that specific purpose, and please keep your transactions so short, might be the way to achieve that. But as I say, most of the use case, you will be good with read committed. And in Postgres world, as I already say, there is no such thing as read and committed. Of course, you can play with set isolation level to read and committed, but behind the hood, it will do read committed. So that's not very useful. It was only created for SQL compliance. And actually, that's kind of all I have. But again, just keep in mind that most of the time you don't need all that. And that's why most of you can have been very successful in your work without knowing all the things. But there are some specific use cases where it can be very useful to know that, to understand better how it works and how you could set it to a better level so that you can avoid some anomalies that are a problem in your specific use case. So do you have any questions? I know it was difficult to follow without the slides, but feel free to reach out to me after or during the party or whatever. I forgot to mention one thing about me. I'm also the founder of Postgres Women. So if you're interested in becoming an allies, or if you're a woman and would like to know what Postgres Women can do for you, I'm here and you can come to me and ask any question. Thank you.